Have you ever had that light bulb moment, a brilliant idea for an app or a program, but then you just stop? You get stuck wondering, how do I actually tell a computer what I want it to do? Well, today, we're going to break that down. We're talking about the journey from a human idea to a set of crystal clear instructions a machine can follow. This, my friends, is the essence of computational thinking.
So how does that actually happen, right? How do we bridge that gap between our creative, sometimes kind of messy, human thoughts and the super rigid, logical world of a computer? The answer, and this might surprise you, is a structured, step-by-step process that starts way before you ever write a single line of code.
You can think of the whole thing as a translation. We're taking an idea and turning it into a visual plan, and then translating that into a written plan. It's kind of like how an architect creates a detailed blueprint before anyone even thinks about pouring the foundation for a house.
And that brings us right to that first and honestly probably the most important step, the visual blueprint. Here's the little secret from the world of pro-level programming. The best programs aren't built on code first. They're built on a solid visual map of the logic.
That blueprint has a name. It's called a flowchart, and it's an incredibly powerful tool. It uses a universal set of symbols to lay out the step-by-step flow of your logic. The whole point is to make the plan so clear that anyone can look at it and just get it in a second.
Now, these shapes are like a universal language for problem solving. You've got the oval, which is your start and finish line. The parallelogram is all about communication, getting information in or sending results out. The rectangle, that's your workhorse. It's where all the action, like calculations, happens. But the real star of the show is the diamond. That's the brain. It's where your program asks a question and makes a choice, splitting the path. That simple shape is the heart of all decision-making in software.
Okay, let's put this into practice. Say we want to solve a simple problem. Find the larger of two numbers. You can see how a flowchart makes this crystal clear. You'd start, get the two numbers as input, hit that decision diamond to ask, is the first number bigger? And then follow one of two simple paths to show the right answer before stopping. See? That visual clarity makes sure your logic is solid before you even think about code.
All right, so once our visual map is locked in and looking good, it's time to translate that picture into words. And that brings us to our next stage, writing the instructions. This is the bridge. We're moving from the flowchart, our visual plan, over to something called pseudocode, which is going to be our written plan. It's the perfect next step to get us closer to an actual working program. So what in the world is pseudocode? Honestly, just think of it as a draft of your program written in plain, simple English. The best part is it's not a real programming language, so you don't have to worry about all the picky rules like semicolons or brackets. It's all about focusing purely on the logic. It's a tool for you, the human, not for the computer.
And here's a brilliant example of that. Just look at how clear this is. That phrase, while there are cards in pile 1, that's setting up a loop. And the instructions inside, simple, clear actions. It perfectly describes a process without a single bit of confusing code. Anyone can read this and know exactly what's supposed to happen.
Okay, so we've got our visual plan and we've got our written instructions. But instructions can't just operate on thin air. They need something to work with. They need information. In our world, we call that data.
And this leads us to a really critical question, because for a computer, not all data is the same. It absolutely needs to know what kind of information it's handling. Are we talking about a number? Are we working with a word or a name? Or is it a simple yes or no answer?
And that's where we get into data types. The three big ones to know are integers, your basic whole numbers, strings, which are just sequences of characters like a name or a city, and booleans, which are super simple. They can only be true or false. And hey, remember that diamond shape in our flowchart? That's powered by booleans. That's what it's checking for, a true or false condition.
So those data types are great for single pieces of info. But what if you've got a whole bunch of them, like all the test scores for an entire class? You're not going to handle those one by one. You need a way to group them together. That's where collections come in. And the most common one you'll see is a simple list. It's just a container to hold multiple items in order.
And what's really cool is that you can perform operations on these lists. For example, you can easily combine two of them into one. As you can see here, we're just taking everything from list A and tacking on everything from list B to make a new, bigger list. It's a simple idea, but it's an incredibly powerful way to manage lots of data at once.
All right, let's pull all these pieces together. We've looked at the visual blueprint, the written instructions, and the data they work on.
Now, let's trace that complete path from the initial idea all the way to a program plan.
We started with our visual plan. That flowchart gave us a perfect bird's-eye view of the logic for our problem, right? No confusion, no ambiguity, just a clear map for finding the larger number. And from there, we built our written plan. The pseudocode took that visual flow and turned it into simple, step-by-step instructions that anyone can understand. It's that final, crucial bridge you cross just before you start writing actual code.
So why does all of this matter? Why go through all these steps? Because this way of thinking saves you from a world of headaches. A flowchart forces you to find flaws in your logic early. Pseudocode makes you clarify every single step. And knowing your data types means you won't accidentally tell the computer to, multiply someone's name by their city. This structured thinking isn't just some nice-to-have technique. It is the absolute foundation of all great software.
So there you have it. We've just walked through the fundamental framework for taking any idea, no matter how big or small, and turning it into a logical, solvable process. You now have the core tools to think like a programmer. The only question left is, what problem are you going to map out first?